Hello and welcome to this short proof that the mathematical constant e is less than the number 3. So if you are not coming from my video on the number e, you might not get the context, but e is a mathematical constant and its formula is this. E is the value of the limit as n goes to infinity, or as in a really large number, of 1 plus 1 divided by n to the power of n. This is the value of e. And to do this proof, we are going to consider n being an element of the positive integers. So we are going to only consider integer n's. This is of course not a problem because as n goes to infinity, integers and non-integers, it doesn't really matter, it's just a really big number. So let's now consider how we can show that this number e is less than 3. To start off, we are going to observe that here we have one term plus another term to the power of n. So what we have here is a binomial, which means we can use the binomial formula to solve this thing. If we take the binomial, and I'll refresh you with this, a plus b to the power of n is equal to the sum, as r goes from 0 up to n, of n choose r times a to the power of r times b to the power of n minus r. This is true, and we can use this for integer n's. So because we are limiting our n to integers, we can do this, not a problem. So that means that e is the limit as n goes to infinity of, considering this thing and applying the binomial theorem, let's say that this 1 divided by n is our value a and this 1 is our value b. And then this n is of course our power n in this case. Meaning if we substitute these values into this binomial equation, what we get is that this is the sum of r equals 0 up to n of n choose r. Instead of a we put 1 divided by n, so instead of a to the power of r we have 1 divided by n to the power of r times, and then b is 1, so we have 1 to the power of n minus r. So here I'm going to really quickly remove this 1 here, because 1 to the power of any integer or any number for that matter is equal to just 1, and 1 times anything is equal to that same thing. So 1 times this whole thing is just equal to this whole thing. I'm going to write on the next line, this is equal to the limit as n goes to infinity of the sum from r going to 0 up to n of n choose r. And now I'm going to do another simplification. 1 divided by n to the power of r is 1 divided by n to the power of r. So we've gotten rid of this 1 because anyway multiplying by 1 does nothing. So we're going to remove it. Now what we have is that e is the limit as n goes to infinity of the sum as r goes from 0 up to n of n choose r times 1 divided by n to the power of r. Now what we're going to do next is substitute this n choose r in terms of functions that we know. For those of you who might not be aware, the function n choose r, sometimes written like this, n and r inside like a bracket, this kind of thing, is n factorial divided by r factorial times n minus r factorial. And for those of you who might not be aware what the factorial function is, x factorial is defined for integer x as x times x minus 1 times x minus 2 times all the way down until we get to 3, 2 and 1. It is of course possible that you take the factorial of like 3, in which case it's just these 3 terms, or factorial of 2, in which case it's just these 2 terms. So that is the definition of x factorial for some value x. Furthermore, it should be noted that 1 factorial is defined as 1 and 0 factorial is defined as 1. So this might sound a little weird, but 1 factorial is equal to 1 and 0 factorial is equal to 1, and higher factorials can be found by this formula. So using this knowledge, let's now replace the choose function up here. So replacing the choose function, we have that e is equal to, I'm going to put this in a box because this is not part of our solving, it is something that we use to simplify our solving. So taking this thing that we have written up here down, this is equal to the limit as n goes to infinity of the sum of terms as r goes from 0 up to n of, instead of n choose r here, we're going to write n factorial divided by r factorial times n minus r factorial. And then this thing needs to be multiplied by this last term, which is 1 divided by n to the power of r. So we have that, and now using the second part of knowledge that we have, what the factorial function is, we're going to expand this once again by expanding n factorial and n minus r factorial. We are not going to expand r factorial because we don't need to. You will see why we're not going to expand r factorial. So let's rewrite it. We have the limit as n goes to infinity of the sum of r going from 0 up to n of n factorial based on our definition of the factorial function is going to be n times n minus 1 times n minus 2 all the way down up to, I'm going to have n minus r in the middle somewhere here. I'm just going to write that n minus r, then on the left of n minus r we're going to have n minus r plus 1, and on the right of n minus r we're going to have n minus r minus 1. We're going to go down even further up to 2 and 1. You'll see why I added this little part in the middle as well. It's so that I can do some nice cancellation. This whole thing needs to be divided by r factorial, which I'm going to leave as r factorial, but I'm going to expand n minus r factorial. N minus r factorial is n minus r times n minus r minus 1 times n minus r minus 2 all the way down up to 2 times 1. This whole thing needs to then be multiplied by 1 divided by n to the power of r. So here, look at the denominator and look at the numerator and look at what kind of cancellations can happen. In this case, n minus r could cancel to n minus r minus 1 could cancel to n minus r minus 1. This could happen all the way down until we get to 2 and 1. So all of this gets cancelled out. Removing all of the cancelled out terms, what we are left with is the limit as n goes to infinity of the sum of r equals 0 up to n of n times n minus 1 times n minus 2 times all the way down until the very last term that didn't get cancelled, which is n minus r plus 1. This thing is to be then be divided by r factorial and another n to the power of r. Now I'm going to do another clever thing. I'm going to distribute this n to the power of r across each of these. Because r is an integer, I can do this without a problem, so I'm going to distribute it. So doing this, first I want you to do an observation. I want you to check how many terms we have left on the numerator. So considering the number of terms we have left on the numerator, if this is term number 1, term number 1 can be identified by having n minus r plus a 1 here. The very next term, which I'm going to label term number 2, would have to be n minus r plus 2. It can be identified by the fact that we have n minus r plus another 2 there. So we have the third term being n minus r plus 3, the fourth term being n minus r plus 4, and so on all the way down. So in general, what we have is n minus r plus something. So if we can find how many if we can count the number of terms here, the very last term would be n minus r plus something, and that last term is n. So what we have is that n is n minus r plus some k, where k is the total number of terms. So we can say that this is also equal to n, which means that cutting this n with this n, minus r plus k is equal to total of 0. Meaning that k is equal to r. So what does this tell us? This tells us that there are r number of terms on the numerator. We have r number of terms in total on the numerator, starting from n, and if you count n as 1, 2, 3, 4, 5, 6 all the way down, the very last term that we count will be the rth term. So using this knowledge, I'm going to do something clever. We're going to take the limit as n goes to infinity of the sum r equals 0 up to n. I'm going to distribute this n to the power of r, because recall, n to the power of r is n multiplied by itself r number of times. So I'm going to distribute this, and I'm going to say this is n times n minus 1 times n minus 2 times dot 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 all the way down up to n minus r plus 1. And I'm going to distribute this n to the power of r as r number of n's. So because we have r number of terms on the top and we have r number of n's on the bottom, I can pair up these and give each of the terms on the top its own personal divide by n. So I'm going to do that. This thing can be divided by n, this thing can be divided by n, this thing can be divided by n all the way down. Every single term can be divided by n. After that, I have now distributed the n to the power of r term. I still have to write the r to factorial term, so I'll write that as times 1 divided by r factorial. So here, because I had r number of terms on the top and I had r number of n's on the bottom, I could distribute them such that every single term is some number divided by n. So the first term is 1 because n divided by n for any n that's not 0 is equal to 1, and because n is going to be a very big number as n approaches infinity, n is definitely not 0, so this is totally fine. If we consider the next term, we have n minus 1 divided by n. So if we consider some finite simple example of this could be something like 6 minus 1 divided by 6, which is 5 divided by 6, which is 0.83 repeating, which is less than 1. This next term is also going to be less than 1. However, when n gets bigger, for example, if we set n to be 100, 100 minus 1 divided by 100 is equal to 99 divided by 100 or 0.99. Now it's still less than 1, but you can see this thing is getting closer and closer to 1. When we get to a very big n, like n approaching infinity, we cannot be certain that this number is actually less than 1. In fact, as n approaches infinity, n minus 1 divided by n is said to be equal to 1. So because of this, as n approaches infinity, because n is not necessarily infinity yet, we can say that this term is at least less than or equal to 1. Similarly, the next term is also less than or equal to 1. It could be equal to 1 if n is sufficiently large. So then this term also n minus 2 divided by n by the same exact logic could be equal to 1, but it's most definitely either equal to or less than 1. We can do this for all the terms in the middle, including the last term here. So this term here is also less than or equal to 1. So then we have a whole bunch of numbers that are less than or equal to 1 and another number which is equal to 1 times r factorial. If I write this out, we have that e is equal to the limit as n approaches infinity of the sum of all terms starting from counting r equals 0 up to r equals n, and we have 1 times something that is less than or equal to 1 times something that is less than or equal to 1 times dot 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 all the way down times something that is less than or equal to 1 times 1 divided by r factorial. So here we have a bunch of terms that are all less than or equal to 1. If we multiply all of these together, the final number we get is also going to be less than or equal to 1. So here we have less than or equal to 1. That means this entire term is less than or equal to 1. Now, what we have is 1 divided by r factorial times some number which is less than or equal to 1. So therefore, when we multiply these, we get that the final number that we get is less than or equal to 1 times 1 divided by r factorial, which is less than or equal to 1 divided by r factorial. So therefore, this whole term that we have inside of the sum is less than or equal to 1 divided by r factorial. What this means is that e itself is less than or equal to 1 divided by r factorial sum given these sum conditions. So we have that e is less than or equal to the limit as n approaches infinity of the sum of r equaling 0 up to n of 1 divided by r factorial. In fact, this equal to becomes important because actually, factually, e is in fact equal to the limit as n goes to 0 in infinity of the sum r equals 0 up to n of 1 divided by r factorial. We are not going to get into that right now, but this less than or equal to, the equal to part is quite important. But that's not going to be relevant for our proof here. we are simply going to now consider this equation. E is less than or equal to the limit as n goes to infinity of the sum r equals 0 up to n of 1 divided by r factorial. I am going to take a couple of terms out of this sequence. In this sum here, we are starting from r equals 0 up to r equals n, which means that we have to do r equals 0, r equals 1, r equals 2, r equals 3, r equals 4, all the way up to r equals n. So here I'm going to take out a couple of terms. I'm going to say that e is less than or equal to the limit as n goes to infinity of the sum of r equals 0 up to n is equal to the sum of r equals 0 up to 2 of 1 divided by r factorial plus the extra bit from r equals 3 all the way up to infinity, right? So in this case n of 1 divided by r factorial. So here you might be wondering why there's a 2 here and why there's a 3 here. It's because this sum operation is a discrete property. We are going from r equals 1, 0, 1, 2, 3, 4. If I want to break this, I cannot break this in the middle of 2 because then I would be overcounting 2 twice. A lot of people tend to make this mistake. It's not like integration. Summation is a discrete operation, which means you cannot have the same ending and starting points when you break a sum into 2 pieces. So here, this thing counts all the r's from 0 to 2, as in r equals 0, r equals 1, r equals 2, and the second one counts all the r's after that. So r equals 3, 4, 5, 6, and so on. Together, both of these count every possible r. This one counts 0, 1, and 2, and then this one counts after that 3, 4, 5, 6 up to n. So here we have a complete field. This is covering all the possible r's. The left hand side is finite. We can take this thing and express it as a finite sum. The right side, however, is infinite because n is approaching infinity. So we're going to avoid that and we're going to break this sum into 2 pieces and apply the limit to each side. The limit doesn't matter for the left side because anyway there's no n dependency here. So I can directly write that e is less than or equal to sum of r equals 0 up to 2 of 1 divided by r factorial plus the limit as n approaches infinity of the sum of r equals 3 up to n of 1 divided by r factorial. This is exactly the same as this expression here. It's just that we're taking the first few terms out of our limit. So, the first few terms, what are they? The first few terms are what happens when r equals 0, what happens when r equals 1, and what happens when r equals 2. Substituting into here, we have 1 divided by r factorial when r is 0, which is 0 factorial, plus 1 divided by r factorial when r is 1, which is 1 divided by 1 factorial, plus 1 divided by r factorial when r is 2, which is 1 divided by 2 factorial, plus the rest of it, which is the limit as n goes to infinity of the sum of r equals 3 up to n of 1 divided by r factorial. These first few terms, we can easily see this first term is equal to 1 divided by 0 factorial. 0 factorial, recall, is defined as 1. So therefore we have 1 divided by 1 here, which is just 1. Plus 1 factorial is also 1. So 1 divided by 1 is equal to 1. So we have another 1 here. Plus. And then we have 1 divided by 2 here, 1 divided by 2 factorial here. 2 factorial is 2 times the previous number, which is 1, times nothing else. So 2 times 1, which is just 2. So we have 1 divided by 2, which is a half. Plus the limit, of course, as n approaches infinity of the sum of r equals 3 of times up to n of 1 divided by r factorial. E is less than or equal to this quantity. So here I am now going to direct your attention to this sum here, and I'm going to replace this thing with a completely different sum. For this proof that we're going to do just now, we're going to require mathematical induction. So I'm going to tell you that 1 divided by r factorial is going to be less than 1 divided by 2 to the r minus 1 for r's greater than or equal to 3. And to prove this fact, I'm going to instead write this in another format to say that r factorial is greater than 2 to the r minus 1 for r's greater than or equal to 3. To prove this fact, I'm going to use mathematical induction. So to do mathematical induction, if you're unfamiliar with how mathematical induction is done, it's done something like this. We take a starting index and test for it. So let's say we check if it's true for r equal to 3. Because in this case what we're doing, we're claiming that it's true for r greater than or equal to 3, which means our best starting case would be the fact that it should be true for r equals to 3. So we'll try that. We'll check what happens when r is equal to 3. The left hand side is r factorial, which is 3 factorial, which is 3 times the previous number, which is 2, times the previous number, which is 1, which is 3 times 2 is 6, times 1 is still 6. So it's 6. The right hand side, on the other hand, is 2 to the power of 3 minus 1, which is 2 to the power of 2, which is 2 times 2, which is 4. Because we have that the left hand side is greater than the right hand side, i.e. 6 is a number that is greater than 4, it is true for r equals 3. So we make the statement that is true for r equals 3. We have shown that is true for r equals 3. The next step in mathematical induction is to assume that this result is true for a certain number and then show that it's true for the next number. So we're going to do that in the next page. What we want to show is that r factorial greater than 2 to the r minus 1 for r greater than or equal to 3. So let's assume that it's true for some number which is greater than 3. So what we do here, we assume that for r equals some number which I'll call p, where p is a positive integer same as r, and p is greater than the minimum value of r, which is 3. For these conditions, let's assume that it's true. So we'll assume that p factorial is in fact greater than 2 to the p minus 1. This is our assumption. We're assuming that this is true, and we're going to use this assumption to show that if this thing is correct, if it is true for r equals p, it's then true for the next number, which is r equals p plus 1. So we'll then check r equals p plus 1, the very next number that we want to consider. So here, for the very next number, what we get is that the LHS is equal to p plus 1 factorial. So p plus 1 factorial is equal to p plus 1 times the previous number, which is p, times the previous number, which is p minus 1, times the previous number, which is p minus 2, all the way down. Now you can see something interesting here. If I write this out, p plus 1, if you know factorials, you of course know that this is true. This is p times p minus 1 times ... all the way down to 2 times 1. This thing right here is p times p minus 1 times p minus 2 times the previous number until 1, which is exactly what p factorial is. So therefore, what we have here is that p plus 1 factorial is equal to p factorial times p plus 1. So we have p plus 1 times p factorial. Now we make the observation. Since p is greater than 3, p plus 1 must be greater than 4, because, well, if p is greater than 3 and we add some 1, we add 1 to some number that is greater than 3, we should get some number that is greater than 4. So therefore p plus 1 is greater than 4. So I'm multiplying p factorial by some number that is greater than 4. Therefore this product must be greater than 4 times p factorial. On the right side, if we consider what the RHS is, the right side is 2 to the power of p plus 1 instead of p here, instead of r, we substitute p plus 1 minus 1. Which, if we rearrange the indexes, it is 2 to the p minus 1 plus another 1. You can see, if we just rearrange this thing, we can get that this is also the same thing as 2 to the p plus 1, so 2 to the p minus 1 plus 1. So in indexes, 2 or any index, any base to the power of 1 index plus another index is that base to the first index times that base to the second index. So in this case, if I group the p plus 1 and I group the plus 1, this is, if I group the p minus 1 and the plus 1, 2 to the p minus 1 times 2 to the 1 is equal to 2 to the p minus 1 plus 1. So therefore this is equal to 2 times 2 to the power of p minus 1. So we have this. So therefore, considering the fact that 4 is in fact greater than 2, we have that because we assumed that p factorial greater than 2 to the p minus 1, we can say was assumed. And because we now have that 4 is greater than 2, if we multiply the two left sides together and the two right sides together, the left side we have two bigger numbers multiplied together, which is still definitely going to be greater than the two smaller numbers multiplied together. This is like a fundamental concept. If you multiply two bigger numbers on the left hand side by each other, it's still going to be bigger than the two smaller numbers on the right hand side. So therefore, 4 times p factorial is going to be greater than 2 times 2 to the p minus 1. And because we have that p plus 1 times p factorial was greater than 4 p factorial, which is then greater than 2 times 2 to the p minus 1, we have that p plus 1 times p factorial is going to be greater than 2 times 2 to the p minus 1. What is p plus 1 times p factorial? Well, it is p plus 1 factorial. What is 2 times 2 to the p minus 1? Well, it is, as we found earlier, 2 to the p plus 1 minus 1. So therefore, we have proven it for the next number. Here we had the form r factorial greater than 2 to the r minus 1. We checked it for some number p, and we found that if it was true for p, then substituting the same exact way, instead of r, if we substitute p plus 1, we can see it's still true. So by the fact that when we assumed that it was true for some number p, that where p was greater than 3, we found that it was also true for the very next number p plus 1. So this is fact number 2. When we assumed it for p, we found that it's true, which is fact number 3, for p plus 1. So by these three concepts, we can see we found that it's true for 3. And we know if it's true for some number p, it is then true for the next number. I actually made a mistake here. I should have said p greater than or equal to 3. In which case, actually here, what we have is that this is greater than or equal. In which case, over here also, this is a greater than or equal. And then finally, this is a greater than and that. I apologize for that mistake. I require the equal sign there because I need to be able to go from 3 to the next number. I just realized that just now. So, what we have proven here is that we know that this value here, this equality here, this inequality is definitely true for 3. We also know if it is true for some number p which is greater than or equal to 3, which 3 is greater than or equal to 3 because 3 is equal to 3. Given that this is true for a certain p which is greater than or equal to 3, we know that is equal for p plus 1. So in this case, 3 is greater than or equal to 3. Because we found it true for 3, we can say it's true for the next number, which is 3 plus 1, which is 4. So it's also true for 4. Now we know it's true for 4. Because we know it's true for 4, we know that, and also that 4 is greater than 3, we know that it's going to be true for the next number, which is 5. So it's true for 5. Because it's true for 5, you can see it's going to be true for 6 by the same logic. If it's true for 6, it's going to be true for 7. It's going to be true for all the numbers after that as well. So it's going to be true for all the integers greater than 3, inclusive of 3. So now we can see that p plus 1 factorial is greater than 2 to the p plus 1 minus 1, which means that given this thing, r factorial is greater than 2 to the r minus 1 for all r's greater than or equal to 3. So then, given this, given that we have now proven that, well, we'll put a hence here, hence r factorial is greater than 2 to the power of r minus 1 for r's greater than or equal to 3, we can say that 1 divided by r factorial now is less than 1 divided by 2 to the r minus 1 for r's greater than or equal to 3. This is of course true because both of r factorial and 2 to the power of r minus 1 are positive numbers, so it's true. We are going to use this fact to change our sum from earlier. Recall this sum. I'm going to call this number 4 actually, because I already used 1, 2 and 3. So this is equation number 4. We're going to go back over to here. We're going to go back to the final where we ended our sum. We said that e is less than or equal to 1 plus a half plus this thing right here. So rewriting this thing, we will actually copy paste it. We'll copy this thing, Control C. We'll go down here. Once we've done this sum, now we can, once we've done this proof, we can now repaste it back here. Now, because 1 divided by r factorial is less than 1 divided by 2 to the r minus 1 for r greater than or equal to 3, over here, whatever this limit is, it is going to be less than the limit as n goes to infinity of the sum r equals 3 up to n of 1 divided by 2 to the r minus 1. Why? Because every single term of 1 divided by r factorial is going to be less than every single corresponding term of 1 divided by 2 to the r minus 1. If every single term is less, it means that the sum is less. So here what I mean is, for this thing, 1 divided by 3 factorial plus 1 divided by 4 factorial plus 1 divided by 5 factorial dot 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 is what the top sum is. The bottom sum is 1 divided by 2 to the r minus 1. So here we have 1 divided by 2 to the 3 minus 1 plus 1 divided by 2 to the 4 minus 1 plus 1 divided by 2 to the 5 minus 1 dot dot dot. Since for each of these terms the bottom term is bigger, their sum, considering their sum, the bottom term is still going to be bigger. Therefore, we can say that this thing which I have just written, where the limit as n goes to infinity of the sum of r equals 3 up to n of 1 divided by 2 to the r minus 1 is definitely going to be bigger than whatever this limit is. Now, we are almost done. We have almost proven that e is less than 3. So, replacing this less than sign into this equation up here, we can see that e is definitely less than 1 plus a half plus the limit as n goes to infinity of the sum of r equals 3 of 1 divided by 2 to the r minus 1. So instead of writing this in this limit form, I'm actually going to write it out as a sum. So what is this sum? Well, the very first number we need to consider is what happens when r equals 3. When r equals 3, substituting that into here, we have 1 divided by 2 to the power of 3 minus 1, which is 1 divided by 2 to the power of 2, which is 1 divided by 4, plus the very next term we have to consider here is what happens when r equals 4. When r equals 4, we have 1 divided by 2 to the power of 4 minus 1, which is 2 to the power of 3, which is 8. So we have 8 here. Plus the next term is of course going to be 2 to the power of 4, which is 16, plus 2 to the power of 5, which is 32, plus dot 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 all the way down. This goes infinitely in this direction. Now, we are almost finished here. We just need to consider what this sum is equal to. So I'm going to do a little thing here. I'm going to say e is less than 1 plus, and I'm going to take this other 1.5 into this sum here. So I can say this is equal to 1 plus a half plus a fourth plus an eighth plus dot 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 all the way up to infinity. So I'm going to call this sum s, and I'm going to bring it aside for a second. If this is the sum s is equal to 1 plus a half plus a fourth plus an eighth plus dot 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 all the way down. Consider what this is equal to. This stuff is a half plus a fourth plus an eighth plus so on and so forth, which is 1 plus a half plus a fourth plus an eighth plus and so on, the whole thing divided by 2. Would you agree to this? Well, of course, the first term, a half, is 1 divided by 2. The second term, which is a fourth, is a half divided by 2. The third term, which is an eighth, is a fourth divided by 2, and it is true for all the numbers after that as well. So therefore, this thing must be true. What is this? Well, this is simply s. Right? This is simply s here. So that means that s is equal to 1 plus this whole thing, which is s divided by 2, because every number after this constitutes s divided by 2. So s must be equal to 1 plus s divided by 2. Subtracting s divided by 2 from both sides, we can see that s divided by 2 must be equal to 1, implying that s is equal to 2 times 1, which is 2. So therefore this sum s is equal to 2. Substituting that into here, we get that e is less than 1 plus s, and s is 2. So we have e is less than 1 plus 2, which is 3. So therefore, as a final conclusion to this video, e is going to be less than 3. We had to use a lot of different techniques here. We had to expand the binomial of 1 plus 1 divided by n to the power of n. Then we had to take each of those individual terms, extract them out. Then we had something like n divided by n times n minus 1 divided by n times n minus 2 divided by n, and so on. We say that each of these terms is going to be less than or equal to 1 because n is going to infinity, which means there's a possibility for a very large n that our product of n minus 1 divided by n and n minus 2 divided by n and so on could potentially be 1. So we just kept on the safe side and said that this is less than or equal to 1. Then taking that sum, we then expanded that sum outward. We considered each of the terms in that sum, and we eventually ended up with this thing of the limit as n approaches infinity of r equals 3 to n of 1 divided by r factorial plus the first 3 terms. I extracted them because for the next bit I required something where r is greater than or equal to 3. Because the first 3 terms violated this, because the first 3 terms had r less than 3, we extracted them out and considered only the last bit. Then for this we used induction, mathematical induction, to show that r factorial is greater than 2 to the r minus 1, r greater than or equal to 3, implying that 1 divided by r factorial is less than 1 divided by 2 to the r minus 1 for r greater than or equal to 3. We then use this to turn one sum into something that is strictly less than some other sum. Using this sum, we found that e is definitely less than this expression here. We then converted this thing into a certain sum, found the sum within itself, replaced that within it, and found that this sum of 1 plus a half plus a fourth plus an 8 and so on is equal to 1 plus itself divided by 2. Then solving that, we found that this infinite sum is equal to 2, and finally substituting that value, we found that e was less than 1 plus 2. Therefore e, the mathematical constant e, which is the limit as n approaches infinity of 1 plus 1 divided by n all to the power of n, is definitely, without a doubt, 100% certified by mathematics, going to be less than 3. So that's it. That is the conclusion of this video. You can, if you came from the video about e, you can go back to that. If not, thank you for watching and goodbye.